Last chance to ask. 26 through 32. Any of these? Which one, Yanji? Thank you for asking a question. That is not 26 through 32. I already went over problems from that yesterday. Remember I said, before we take this quiz, do you want to go over any from yesterday's homework? And I worked a few of those. I can't work all of them because I'm grading that one. So, 26 through 32, last chance. Okay, today's lesson is a new lesson. It's our last lesson of the unit. Okay, Angie, if you work these and you ask me a question from here, I'll work one, okay? I'll do it at the end of class because you didn't give me a number to work, so I'm going to keep moving. So, what do y'all think of when you hear of the word mean? I mean, not like Mean Girls, but like mean in the context of math. So don't be funny. Average, okay? How do you find the average of two numbers? Carson says add and divide. Add them up and divide by how many numbers you have, right? X plus y divided by 2. Okay, so what would be the mean of 4 and 10? Okay, so when you think of mean, you are probably thinking of an arithmetic mean. But there are other means out there. When you think of mean, you're probably thinking on a number line, if I've got 4 and I've got 8, what is the middle of 4 and 8? Well, it's 6. So that is like the one-dimensional, like on a number line, middle of two numbers. That's an arithmetic mean. So that's algebra. That's the algebra mean. But there are other means out there. There's such thing as a geometric mean. And it is derived from similar triangles within a right triangle, and I'm going to show you that later. But what happens with a geometric mean is instead of adding the numbers and dividing by 2, we multiply the numbers. We multiply the numbers, and what do you think? What do you think we do with them then? We multiply the numbers and I took addition and I amped it up and I went to multiplication. So I'm going to take division, I'm going to amp it up, and I'm going to yes, Mean John, very good. So the geometric mean of two numbers is the square root of their product. And that's of two numbers. The square root of their product. So instead of instead of adding and dividing, we are multiplying and square rooting. So how would you find the geometric mean of three numbers? We're not going to do this in this class, but it's good to know. How do you find the geometric mean of three numbers? Cube root, very good. So you would multiply them. I just made that up. And you would cube root because the product is of three numbers. Very good. Okay, so that's what a geometric mean is. Who uses geometric means in the real world? Why do we have them? So if you were comparing two things, like you were comparing 4 out of 10 and 8 out of 10, then it makes sense to add them up and divide by 2. But what if you are, and I got this from Wikipedia, I have to be honest. What if you are comparing two companies? And Company A and Company B are being rated on their environmental sustainability. So how nice are they to the environment? And that's a 1 to 5 rating. And then they're being rated on employee happiness. Are their employees happy? And that's a 1 to 20 rating. So when we score them, they're out of two different numbers. There's two different ranges. So they use geometric means to compare the two companies if they're being rated on two different systems out of two different numbers. So a geometric mean would help kind of fill in the gap of these are out of two different things. If they scored a 4 here, that's 4 out of 5. And if they scored a 15 here, that's 15 out of 20. Doing 4 plus 15 divided by 2 is not going to mean anything because the 4 and the 15 have different weights. Okay, so I've gone on enough of a tangent. That's how they use it in the real world. That's not how we're going to use it in class today. So in class today, we're going to find the geometric mean, but it's going to be in the context of triangles, okay? Go ahead and write this down. This is the actual definition. For any two positive numbers, yes, they have to be positive, A and B, the geometric mean of A and B is the positive number, once again, so we're not dealing with negatives, the positive number x such that A over x equals x over B. So that is the geometric mean of two numbers. So if I say x is the geometric mean of 3 and 15, then by definition, 3 over x equals x over 15. So that is what a geometric mean is. X is the geometric mean of 3 and 15. Okay, I'm going to move on. Find the geometric mean of 4 and 9. So I kind of already told you that the geometric mean of two numbers is the square root of their product. So it's tempting for me to just say, okay, take the square root of 4 times 9. But I do want you to know that by definition, the geometric mean is 4 over x equals x over 9. It is a proportion. So we would, of course, cross multiply. X squared equals 4 times 9. 36. And then you know that to solve for x, you do the opposite of squaring, which is square rooting. Now, normally, x would equal plus or minus 6. Plus or minus 6. But remember, by definition, the geometric mean has to be a positive number. So we're going to throw out our negative answer. So x is going to equal only 6 instead of plus or minus 6. Find the geometric mean of 10 and 40. Go. Like I said, it is fine with me if you take the square root of the product, but by definition, this is the actual setup to solve. So we've got x squared equals 400. So we've got x equals plus or minus 20, except we throw out the minus. And so there we go, x equals 20. It was an easy one, yes. Do you see how 20 is not the middle of 10 and 40? Does that make sense? Okay. It's a little bit different. All right, we're going to talk about this triangle for a long time. Let's make this bigger. Maybe. Okay. What can you conclude about this figure? I'm going to ask you some things about this figure. And I'm probably not going to go to that website. I can show you that later. All right. In this figure, I want to look at the large triangle, please. So I want to look at, there we go. Okay. In triangle ABC, well, first of all, what kind of triangle is ABC? I know I'm insulting your intelligence. Yes, it's a right triangle. So what we're doing today only works in a right triangle. What is segment BD called? What is the title or the name for segment BD? Height is good. There's a word, there you go. There's a word that's synonymous with height, and it is altitude, and that's the word that we're going to use. So this is the altitude of the triangle. Okay. In triangle ABC, what is AB called? What is AB called as a part of that triangle, the yellow triangle? No. 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 Thank you. This is a leg. What's the other leg of the yellow triangle? What's the other leg? Yep. Leg, leg. What's AC called? Now you can type that word. What's AC called? The hypotenuse. Okay? There's no official word for this, but what could we name AD? How would you describe AD? I'm not looking for an official word. We just need to call it something because we're going to use it later. So we have to refer to it as something. Helaman, that's actually what we're going to call it. And we're going to call it a segment of the hypotenuse. So the hypotenuse is broken up into two different segments. So we're going to call this one of the segs, and we're going to call this another seg. Like seg number 1 and seg number 2. The segments, the broken up pieces of the hypotenuse. We're going to get into something kind of close to tangency later, but it's going to be adjacent instead of tangent. Okay, let's keep going. Here's a theorem. I don't recommend you write this down, but I do recommend that you understand what it's saying, but I'm not going to give you enough time to write it down. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original and each other. What I'm saying is that when I take a right triangle and I draw the altitude from the right angle, I get 3 similar triangles. That's what I'm saying. ABC, the whole one, is similar to ADB, which is similar to BDC. And they're similar, you can call them similar by angle, angle. Let's just leave it at that. They're similar by angle, angle. Okay, you could pick an angle for this. You would just have to pick one. So you could pick 30 and 60. And then that would make this one 30. And this one's 90, of course. And that would make this one 60. And so you could see that all 3 of those have a 30, 60, and 90 degrees. So they are similar by angle, angle. Okay. So if the triangles are similar, hi, Corey, their corresponding sides are, we've already gone over this a bazillion times. What are their sides? They're not congruent. They're not similar. Proportional. Okay. Boom. Boom. There we go. So, if those triangles are similar, then AD is to BD. So what are we doing? We're doing the long leg is to the short leg as the long leg is to the short leg. So DC. I'm looking at the medium and the small triangle. AD is to BD as BD is to DC. Now wait a minute. Does that look familiar? Didn't we just go over something that kind of looked like that? BD is the geometric mean between AD and DC. So the altitude, let me get a new color. The altitude is the geometric mean of the segments of the hypotenuse. The altitude is the geometric mean of the segments of the hypotenuse. I know this isn't making a lot of sense yet. Don't write this down. This is the technical wording, but we're going to make this easier to write down, okay? The length of the altitude is the geometric mean of the lengths of the two segments of the hypotenuse. So the things I underlined are kind of the important things. The altitude is the geometric mean of the segments of the hypotenuse. Okay. So let's try it. Let me give you a proportion that you can use over and over and over again, okay? This is like a little thing that you can remember, a little quick hint. So the segment, I'll call it seg 1 over the altitude equals the altitude over the other segment. I'll call it seg 2. That way you don't think they're the same segment. So if I am solving for x, the shortcut way, geometric mean is just a shortcut. The shortcut way to solve for x is, let's follow this, segment 1, 2, over the altitude, which is x, equals the altitude over the other segment. So the altitude is the geometric mean between the two segments. So you could have just stared at this problem and said, oh, x is the product, the square root of the product. X is the square root of 2 times 8. But we want to show our work and do things thoroughly, so 2 is to x as x is to 8. But we know in the end we're definitely going to be doing this, which is okay with me if you go straight to that, but you can cross multiply if you want. And what is it? Yeah, x is 4. I'm going to move on. Oh, Helaman saying question mark, question mark. That was earlier? Okay. Okay, whoa, that's a lot of words, Ms. Stanton. Why are you even showing this to us? Okay, I'm showing you the other one. So there's 2 proportions we're going to learn today. We already did segment over altitude equals altitude over the other segment. There's one more proportion that is derived from geometric mean, and here's the paragraph about it. Okay, the altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean. Okay, so the leg is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse adjacent to that leg. Okay. Whoa, that's a lot of words. Let me break that down for you. What that is saying, that's actually one sentence, it's not a paragraph. What that is saying is that the leg is the geometric mean of the hypotenuse and the segment adjacent to the leg. And, let me get another color, the segment adjacent to the leg. So the leg, AB, is the geometric mean of the hypotenuse, AC, and the segment of the hypotenuse that's closest to what you're looking for, to the geometric mean. AD is closer than DC. It's adjacent. Okay. This says the same thing except it uses the other side. So let me give you your other proportion. Let me give you your other proportion that you're using. This one is the leg of the triangle, of the right triangle. The leg is the geometric mean of the hypotenuse and the adjacent segment. So these 2 proportions are pretty much the 2 things you needed to write down today. All right, so this is the geometric mean between this and this. X is the geometric mean between the hypotenuse. What's the hypotenuse? 18. X is the geometric mean between the hypotenuse and the leg adjacent to X. 8. So it's like the whole and the part. The leg is the geometric mean between the whole and the part. The whole hypotenuse and the part that's closest to X. It can be either leg. It can be either leg as long as you choose the section of the hypotenuse that's adjacent to the leg. The more we do these, the more it'll make sense. 12. Very good. It's the square root of 8 times 18. All right, let's draw our own picture. Let's just draw another one that looks similar to the ones we've been doing. The altitude to the hypotenuse of a right triangle divides the hypotenuse into segments of 3 and 27. Find the length of the altitude. So I gave you 2 proportions. You need to always pick the correct proportion depending on what you're looking for. I'm looking for the altitude. So pick the proportion that talks about the altitude. Segment 1 over the altitude equals the altitude over segment 2. Or the geometric mean, the altitude is a geometric mean between the pieces of the hypotenuse. Okay, good job. This is actually the last one of the day. I'm about to run out of time on my recording. I don't know why. Anyways, so there are 3 things we're looking for. I recommend we cover up the other ones and look for one at a time. Let's do the easiest one first. Let's find y.